PID controller tuning, it's all about selecting the correct values for KP, KI and KD. So how much proportional gain should you have, how much integral action should you have, and how much derivative action should you have. So by tuning the values of KP, KI and KD, you decide how the system responds to noise or the changes in the desired value, the set value. You decide how fast the system should be, or the settling time, how long does it take before the oscillation settles to zero. You decide acceptable overshoot, and you also decide the accepted steady state error. And of course there are no preset values that would work with every process. Every process has to have the correct values of KP, KI and KD. So let's go back to the example here, way back to the tank that we had. It's here. If we say, if the tank here, if the level of the tank were to rise up here, well, then the P element changes, and we would need to adjust the PID controller again for the new values that goes with a full tank. So the PID controller tuning is a constant job that has to be done. So process controller engineers, they constantly tune PID controllers to the desired value. So look at this. A high proportional gain will result in a large change in the output for a given change in the error. If the proportional gain is too high, the system may become unstable. A small gain may result in a response, small response, and a less sensitive controller. If it's too low, the controlling action may become too small with its response to disturbances. So you see here for 3 different values of KP. If it's high, it's quicker, but it may become unstable, so there's always a risk. Unstable means that the oscillations will go on forever. The integral term accelerates the movement of the process towards its set point and eliminates the steady state error. But the integral term is responding to accumulated errors from the past. It may cause the system to overshoot the set point. So you see here, if we have more integral, it's faster. The curve here rises much faster, but it overshoots very much. So the red curve here is with the small integral part. The red curve rises slower, but it doesn't overshoot. And the derivative control is used to reduce the magnitude of the overshoot. You see here, the overshoot here is much larger here. For the black curve, you see it has a large area under it. So it's reduced here and it settles faster. The black curve settles slower. The differential of a signal amplifies noise, so it may become highly sensitive to noise if we use the derivative term. This is an animation that we should study. Now first we adjust the proportional gain, then the integral gain reduces the steady state error but makes an overshoot, and the derivative reduces the overshoot to a perfect level here. So the proportional gain alone, the higher proportional gain, less steady state error, but still we have some. The integral gets rid of the steady state error but gives an overshoot, and the derivative gets rid of the overshoot again. But the system becomes very sensitive to noise. So the P control also will increase the risk of oscillations. And if the eye control is too large, you have excessive overshoot. And if the D control is too large, you have the risk of oscillations again, and it picks up noise. So what values should we select for P, I, and D? Well, two engineers, Ziegler and Nichols, they found two methods for suggested values of Kp, Ki, and Kd. So you have some ideas of what you should put into the control law, and then when you have put in the values here, started your system, then you can fine-tune by observing the response. But you need some starting points for those values, and that is the methods of Ziegler and Nichols. So I will briefly go through the two methods. Method number one is called the process reacting tuning method, which is that you break the line here and you give an input directly to the correction element. Remember the tank again, that would be the heater element in the tank, and we give, like, say 500 watts or something to the heater element directly. And then we measure the response here. You can actually take out the measured value here, but this is the true value, and you take a measurement of the true value and use it here. So the idea is, if we have a step response here, a sudden change, that is sent through these three boxes. So by doing that and analyzing the response, we get an idea of what these three do together. And then we can use what we learned from these three boxes to tune that box. And then we reconnect and run the system as normal. So what you do with this system is that you give a step to the correction element, a sudden change in the power, and you analyze the response. And the response would typically be like this, rising up to a new value. If that was to give 500 watts to the tank, the temperature would rise and settle at a new value here. And then you draw some asymptotic lines. Here you have one, and here you have one, and you have the crossing point between the two there, and you have also the crossing point with this line crosses the starting point here. And then you note two things basically. You note the L, which is the latency or the delay of the system, and then you find the value for A, which is the amplification of the system. And then when you found the A and the L from this figure, you use that in a table like this. First you have to decide if you are to use a P control, PI control, or PID. If you use a P control, you should set your K value to 1 over A. So you use the A here. K here is the same as KP. And again, I haven't introduced it yet, but the table doesn't use KP, KI, and KD. It uses K, TI, and TD. And that has to do with the history of PID controllers and what the really old engineers, what they used. They were not mathematicians. They were actually engineers with dirt on their hands, so oil, grease on their hands. So they like to work in the time plane and analyzing how the systems responded to time. Anyways, the TI is the same as KP over KI, and TD is the same as KD over KP. So if you use P control, select the value for KP, 1 over A. If you use PA, Then your Kp should be 0.9 over A, and your Ti should be 3 times L. L is the latency. If you use PID, you need to have values for all three of them. 1.2 over A, 2 over L, and L halves. And for the P control, you actually zero out these two parts here. So you want to zero out your Ki, which means that you set Ti to infinity, because something over 0 would be infinity. So if you set Ti to infinity, you have actually cancelled out the integral part. If you set Td to 0, then the Kd is 0. So you cancel out the derivative part by setting Td to 0. You cancel out the integral part by setting Ti to infinity. So these are the suggested values made up by experience from Mr. Ziegler and Mr. Nichols, and you put that into your system, you start your system, and then you fine-tune based on the response that you see in your process. So if you want to make it slightly faster, maybe you should increase the TD a bit, for example. And then they had another method, because it's not always that it's possible to break the system here in that part here. If it's not possible to do that, you need to use the other method that they have, and it's called the ultimate cycling tuning method. And the idea here is to give a small disturbing by changing the input. So you give a small disturbance here, short disturbance, and you analyze the response from here. Remember that the loop is now closed. And you adjust, you also start by setting Ki and Kd to 0, which means Ti to max and Td to 0 actually. You generate a small disturbance to the input, and then you adjust Kp until you have stable oscillations. Look, first you generated the disturbance, and you see the K was set to 3, which was too small because the oscillations here gradually decreases. Then it was increased to 4, and you see now the oscillations increase, which means too high. And then it was set to 3.5, and then you had stable oscillations, which means that you have found your ultimate Kp. It's not ultimate for all purposes, but it's the Kp that is giving those steady oscillations. So you call that Ku, and you also note the period time of the oscillations, and you call that Tu for period time. And again, you put that into your table. If you want P control, your Kc should be selected to Ku halves. So in this case, it would be 1.75, 3.5 halves. If you want Pi control, Ku divided by 2.2, and Pu divided by 1.2. And that one should be selected to 0. And here, infinity, 0. If you want PID control, you set the Ku, the proportional gain to Ku divided by 1.7, Ti to Pu divided by 2, and Td to Pu divided by 8. So you put those values into your PID controller, and then maybe fine-tune based on experience.